Okay, so welcome back. Where we had kind of stopped yesterday, or in the last lecture, was tying in our system with what's called the orbit equation. So, for instance, if we had an autonomous system in the usual notation we introduced yesterday, so if here is my autonomous system, then a solution, right, to this, which would, remember, a solution to a system like this means functions x of t and y of t satisfying those two equations. The big difference here with what we've been doing the entire time is these, of course, are not necessarily linear. This allows for a wider variety of sorts of equations and definitely sorts of behavior of solutions to these things. So anyway, a solution, that is solution vector x of t, y of t, satisfying these two things. This also satisfies what we call the orbit equation. So this implied that right, minus g xy dx dt plus f of xy dy dt is actually equal to 0, as we saw yesterday. So just really quickly, right, if I write this out, since dx dt is f and dy dt is g, dx dt is f, dy dt is g, so I get minus gf plus fg, which is 0, of course. And so we get this thing, which is called the orbit equation, associated to this thing. So clearing denominators here, right, writing this in differential form. I guess I should say differential form, or separated differential form, right? This is what it looks like. Okay, and this is my orbit equation. Okay. And so we saw, of course, like an immediate relationship between what we did all the way back in chapter 1 for these equations of exact differential form type. We had, this, so dy dx could be thought of as g over f, wherever f is not 0. Or we could also rewrite this as dx dy is f over g, wherever g is not 0, right? So these were two distinct ways we could think about this, depending on where these f's and g's are 0. Okay. But this leads us to solving these systems. This is the important bit, using the methods from chapter 1. So this leads us to solving these systems using the methods from chapter 1 with respect to exact differential forms. Okay, so and so we just took kind of the last thing in the course that we're discussing and tied it back to something we did in the first chapter, where we're going to see that solving these systems is going to be the same as solving those exact differential form equations all the way back. Okay, so let's see how this goes. So here's a quick example. So solve the orbit equation for the system dx dt is equal to y, and dy dt is equal to 4x minus x cubed. So we've used this example a couple times now. Alright, so I want to solve the orbit equation for this thing. Alright, so what is the orbit equation? Just going back. Well, if what I have is dx dt is f, dy dt is g, the orbit equation is minus g dx plus f dy. Okay. So then this is minus 4x minus x cubed dx plus y dy is equal to 0. So this is the orbit equation for that system. Okay. Well, this actually is separable. This has a separated differential form here, just by adding this to the other side, right? So if you like, adding this to the other side, this tells me that y dy is equal to 4x minus x cubed dx. Now, this is not always going to happen, right? In fact, in a typical problem, this won't happen, all right? But we have a particularly nice thing where the variables are separated, and they're separated in the right way, right? So one is, they're separated, and they're multiplying the dx or dy things that they depend on. So we got really lucky here. Okay. Well, integrating this, right, like you would do in the case of a separable equation, what do you get here? You get 1/2 y squared is equal to 2 x squared minus 1/4 x to the 4th plus my constant c. Okay, so that's what I get. Alright. Multiplying both sides by 2 and taking a square root. This means that, so this is my implicit solution. Right, you remember that. Finding an explicit solution. Right, so my explicit solution is y of t. I have a choice here. I can take plus or minus the root of 4x squared minus 1/2 x to the 4th plus c. Right, so y is this thing. Okay, so I get two infinite families of solutions. Of course, you might say, oh, well, why isn't this 2c? You can write this as 2c, or you can just say, well, this constant here is not the same as this constant. I absorbed that 2. Okay, in it. All right, so that was pretty straightforward. Okay, but you know, this is, of course, we got a little lucky here. So let's see what happens when we're not quite so lucky. Right, and you know, we'll talk a little bit later, you know, what it is that we're actually doing here. When I found this y, really I found a relationship between x and y here. This one is a little less pure. I've taken the square root, so there's a choice here. So in a sense, I'm going to gravitate a little bit more towards this one. This is a relationship that must be satisfied by x and y in my solution vector. So my solution vector is, you know, x of t, y of t. And so I get a relationship governing how x and y are related to one another. And if I take this and I say, okay, well, really I'm looking for ordered pair whose x and y coordinates are these functions of t. So these functions parameterize the thing in question, and they satisfy this algebraic relationship. This what does this look like graphically, right? X and Y satisfying this relations, this traces out all my trajectories for the system. And so you might say, well, the trajectories of the system, those are my solution curves, right? Those are my solution paths. So really, this gives me a complete description, and we're going to do exactly this example later to see what this looks like. This gives me a complete description of what it is that's going on here, and gives me a plot of every trajectory curve, every orbit in the plane, okay, for this system. All right. Okay. So let's see another example that doesn't work out quite as nicely as this one. Okay. So here's another example. Right, so let's do same thing, but my system instead is dx dt is y plus 9 minus x squared, and dy dt is 2xy. So there's my system. What's the orbit equation now? So the orbit equation is minus 2xy dx plus y plus 9 minus x squared dy. And that's equal to 0. Okay, so this does not have a separated differential form, right? I cannot separate x and y here. Okay, and so how do I solve this thing? Well, I do my chapter 1 stuff. I say here's m, here's n, right? And I check exactness. So I check exactness. Now in checking exactness, I'm checking that the y partial of m is equal to the x partial of n. Let's check that. What's the y partial of minus 2xy? Well, that's minus 2x. Okay, what's the x partial of y plus 9 minus x squared? Oh, it's minus 2x. So indeed, this thing is exact. So what this means is that thus there exists some h of xy such that the x partial of h is equal to m, which is minus 2xy, and the y partial of h is equal to n, which is y plus 9 minus x squared. Okay. Alright, so choose whatever you like here. So how do you want to proceed? Well, I can start with either of these, doesn't really matter. Let's start with this one just because it's shorter. All right, you remember how this goes. So what I do is because of exactness, I know that this process is going to work out. So I integrate both sides of this equation with respect to x. So from this, I get that h of xy is equal to, what is the integral of minus 2xy with respect to x? This would be minus x squared y plus a constant. But remember, I integrated with respect to x. So the most general possible constant here is a little h of y. Okay, so this is the generic form that my big H takes. I'm almost done, but to determine this little h, I need to plug this into my second equation, the equation I didn't use before. So from this, I know that y plus 9 minus x squared has to be equal to the y partial of h, But I'm going to compute the y partial of h from this thing that I found here that I boxed. So what's the y partial of h here? Well, y partial of h is minus x squared plus h prime of y. Right? This is the full derivative of y since little h only depends on y. Okay. And so notice that my x squareds cancel. And so I'm left with the equation h prime of y is y plus 9. Remember, this always happens in these things. This will work out in such a way that you get a first order differential equation that is explicit and easy to do here. So integrating with respect to y, what do I get? I get that little h of y is, what's the integral of this? Is 1/2 y squared. That's 1/2 y squared plus 9y plus constant, right? And so, big H is equal to minus x squared y plus little h, which is this thing, plus 1/2 y squared plus 9y plus constant. And my implicit general solution to this system is given by setting this h function. So this is the implicit general solution to this system is given by setting this h equal to a constant. Or this is me setting, so minus x squared y plus 1/2 y squared plus 9y is equal to constant. Right, where'd the c go? Well, I included it with whatever that constant is. This is my implicit general solution. There it is. Okay. Okay. So, what do I do here? What is this h telling me? Well, again, saying that an implicit general solution is given by this relationship, this is saying that this is a relationship that my solution vector containing components x and y has to satisfy. This gives me a plot, right? This generates a plot, a bunch of curves in the plane. And for different values of the constant, of course, these curves there should be different curves showing up. And these curves should not cross or touch. Okay, so the way that these curves work, they shouldn't cross or touch. Okay, once I have solution, that's it. Okay, you know, I have a thing that is unique, so there can be no crossing or touching by existence and uniqueness, because a crossing or touching point would indicate that you know, you could have two solutions with the same initial condition that are different curves, right? Different trajectories. Okay. So that's what's going on here. But notice that this was also the case in what we just did, our first example. So another way of seeing this, of course, this was a separable equation, so this turned out to be easier. I didn't need to do that whole h business. But it turns out I could have actually rewritten this as some h of xy is equal to constant. If h of xy is 1/2 y squared minus 2x squared plus 1/4 x to the fourth, then this implicit general solution, of course, can be seen to be h is equal to constant. Okay. And so in both of those examples, I could do this. Now, we already know that in general, I can't find such an h, right? Sometimes I can correct that by introducing an integrating factor, but even that doesn't always work, right? So an h of such an h of xy for a system is called a Hamiltonian for the system. Okay, so this is why we've been using that letter big H all this time. I hinted at this. Maybe I even introduced this term back in chapter 1. I can't remember, but this is the reason why we've been calling this thing big H. This is an example of something called a Hamiltonian for the system. Okay. This is an example. This is an example of finding an integral of the system. Now, a Hamiltonian is a special kind of integral. It's a very nice one. But in general, finding an integral for the system is our version of solving it for these sorts of systems. So finding an integral, this is synonymous with solving the system. Okay. All right. Okay. So, for instance, let's say that let me maybe do a quick example of something that does not have a Hamiltonian. So let us try to solve the orbit equation for this other system we worked on yesterday. We found the stationary solutions of anyway. dx dt is y minus x times x minus 1, and dy dt is 3 plus 2x minus x squared times y. Okay. So our orbit equation simplified here is dx dy is equal to y minus x over x minus 1, or sorry, times x minus 1 over 3 plus 2x minus x squared times y. Can we do anything with that? Well, this isn't linear. It's not separable. And it turns out it doesn't have an integral. Okay, so this is not linear. That's not usually a deal breaker right there. Not separable. Also not usually a deal breaker. And turns out it does not have an integral. So we cannot find a general solution to this orbit equation. Thus, we cannot solve. So we cannot find a general solution to this orbit equation. It does have a stationary solution. So it does have a stationary solution, and that's when x is equal to 0, or sorry, x is equal to 1. So it does have stationary solution. X equals 1, however. That's at least something we could say. All right. But yeah, we can't really do anything with this one. Okay. So I mean, it's going to be the case that some of these systems don't have integrals. And you might say, well, what do we do in that case? Well, we can't solve them in that case, but what we can do is apply a type of analysis called a non-integral method, okay, which will allow us to derive some info about the system or about behavior solutions of the system without actually having to solve it. Okay, so here's where the big analogy with what we talked about way back in chapter 1 comes in. These last two sections we're covering are called integral and non-integral methods. Okay, so there's integral methods. And non-integral methods. These are the last two sections we're covering. So what's the terminology mean? Integral methods relies on us essentially solving the system. Relies on us essentially solving the system. Okay. So that is benefit. Okay, so this is good thing. Put a plus there. But also, this is a downside because it relies on us solving the system, and we just saw that this is not always going to be something that we can do. So this is not going to be something that applies to every system. And because it relies on us solving the system, yeah, it's just going to narrow our focus to things we can actually integrate, right? Or, now I'm talking about integrate in the sense of the system, not in actually computing an integral in the, Calc 1 or Calc 2 sense. So when I say integral here, I'm talking about this Hamiltonian thing or something like it. So integral methods rely on us solving the system. That's not always going to be possible, though. So these do not rely on solving. But the benefit here is if we can solve the system in this way, this is going to give us, this gives us basically all the info. Okay. So these integral methods, assuming these systems actually have an integral, this is essentially fully solving the equation. There's nothing left to, or the system, there's nothing left as a mystery. I can basically ask any question about the behavior of solutions and have a way of answering it. Versus the non-integral methods, when we apply them, right, we're not going to have that level of info. That makes sense, of course, because we're not actually solving it. If we could get the same amount of info without actually solving it, well, then we'd probably always do that thing, right? But here, this is good that it doesn't rely on solving the system, but we get less info. Okay, in fact, we're going to see we only get some local info, so mostly we get local info. Around certain points. Okay. All right. And so we are happy to use integral methods when we can actually solve these things. Otherwise, we are basically forced to do something in a non-integral way. You can carry out this analogy between an autonomous equation that we can solve, right? That we can actually find this h for, or we can even maybe use an integrating factor to find a solution to some differential form equation. And then there's some that we can't, right? There's some that we can't. So for something like that, if we wanted to understand what was going on, we would have to use these non-integral methods. Okay. So if I'm dealing with an orbit equation coming from a system that looks like this, okay, This is exact if and only if what is true, the x partial of f is equal to the or minus the y partial of g. Right, so minus the y partial of g. That's just me treating that as m, that is n, and taking the y partial of m, which is minus the y partial of g, and this would be this would have to be equal to the x partial of n, which is f. Okay. All right. So in this case, there exists an h of xy such that the x partial of h is equal to minus g, the y partial of h is equal to f. Okay, and therefore we could rewrite this system. So the system associated to the orbit equation above, that I'll call star, is or can be rewritten as, right, dx dt is equal to f, but f is the y partial of h, and dy dt is equal to g, which is minus the x partial of h. Okay. This is called a Hamiltonian system. So this is a Hamiltonian system. And big H is its Hamiltonian. Okay. The implicit general solution to such a system is the Hamiltonian, h of xy, is equal to constant. Okay, as we've already seen. Okay. Now, let's do this. Let's do this in more generality here in a second. The main thing here is we can use this h of xy to generate a phase plane portrait for the system. One that is very, very, very nice and is going to remind us of what we did for linear systems, drawing phase plane portraits for linear systems, right? That's the big move, right? So we know how to draw phase plane portraits for linear systems, but drawing a phase plane portrait for this system, which is possibly nonlinear, and typically for these problems is going to be nonlinear, but it's autonomous, right? That is our goal. Our goal is to do this from the Hamiltonian. Now, we're going to see both how to do this from Hamiltonian or a slightly more general integral for the system, and then we're also going to see how to do this without reference to those things. Okay, so we can use this to generate a phase plane portrait for the system. We'll see how that works. Okay. Now, more generally, there are conservative systems So let's say that I have an orbit equation of the following form. Now, as we've already seen, an orbit equation is an equation that looks like this. Things like this do not always have a clean solution in the method that we've done. In fact, this exactness condition is key. Say that exactness isn't satisfied. What do I do then? Well, remind yourself of what happens in chapter 1 stuff. I try to find an integrating factor, rho. So my orbit equation becomes a multiplied by rho equation. So minus rho xy g xy dx plus rho xy f of xy dy is equal to 0. This is my orbit equation that I've multiplied by rho. Rho is non-zero, right? So we want rho of xy to make this equation exact, i.e., we want rho of xy to be an integrating factor, as in chapter 1. Okay. Of course, this happens when the x partial of f of xy times rho of xy is equal to minus the y partial of g of xy rho of xy. And we would expand this using product rules here. Okay, for these partial derivatives, right? So typically, to make our life easier at this step, if we were actually doing it, we would make the assumption that rho only depended on one variable. The variable we chose for it to depend on would depend on the complicated, like which thing would make my equation less complicated, basically. So when we can find such a rho, then there exists a function big H of xy such that the x partial of big H is equal to minus rho times g, and the y partial of big H is equal to rho times f. I suppress the notation here, but both of these depend on both x and y typically. Okay. Okay. Such a system has the form dx dt equals 1 over rho times the y partial of h, and dy dt is equal to minus 1 over rho of xy times the x partial of big H again. Okay. All right. This is called a conservative system. So this is a conservative system. So this is called a conservative system because the associated differential form in this case would be conservative. If you remember from Calc 3 what this meant in terms of computing the gradient, then this is, or whether or not your vector field came or appeared as the gradient of some function, this big H is playing the role of that function. Okay, basically. So this is called a conservative system. All right. Notice that our Hamiltonian system from before is an example of this, where rho is equal to 1. Right. So here's our Hamiltonian system, and this is the case rho is equal to 1. So a Hamiltonian system is an example of a conservative system. Okay, but here we have a more general thing where the original equation wasn't exact, but I can seek a rho that makes this exact. In this setting, this h of xy is not called a Hamiltonian for the system. H of xy is called an integral for the system. Okay. And of course, an implicit general solution is again given by h being constant. Okay, so the implicit general solution is h of xy equals constant. So it's solved in the same way from this h. Okay. All right. Okay. So this is my more general setting, as I mentioned. So when we say integral methods, this is something like this is what we're talking about. Okay. Now let's see how I can get phase plane portraits from integrals. So big question. How can I extract phase plane portraits from integrals? So integrals for the system in question. Or Hamiltonians if we're dealing with a slightly nicer system. Okay. So A. All right, my answer is, suppose this is going to be a long answer because it's going to, basically everything we do here for the rest of the lecture is going to follow as an answer to this question. So suppose the system in question is dx dt is 1 over rho of xy h of xy, and dy dt is minus 1 over rho of xy h of xy. So this is my system in question. So it's my conservative system. Rho is not 0 because I'm dividing by it here. Okay. So this also, notice this includes Hamiltonian systems by taking rho equal to 1. So notice this includes all Hamiltonian systems by taking rho equal to 1. Okay. How can I talk about the phase plane portrait? Well, we already saw the first step at the very beginning of this discussion where we found stationary solutions. So in yesterday's lecture we found stationary solutions, but we did this algebraically, right, by just setting each term, right, the f and the g equal to 0 and solving that as an algebraic system. Here we're going to reinterpret those stationary solutions slightly, and we're going to see very easily where this comes from. So first fact. Okay. The first fact is a point x naught y naught is a stationary solution of the system. I'll call this star. If and only if x naught y naught is a critical point of h of xy. Recall what a critical point was for a function of more than one variable. It was a point where the gradient of that function vanished, where it was equal to the 0 vector, i.e. what this means is that the x partial of h of x naught y naught is equal to 0, and simultaneously the y partial of h at x naught y naught is equal to 0. Oh, okay. Well, now it's clear because, I have screwed up here. This is not h here. This would be the x partial, or sorry, this would be the y partial of h. This would be the x partial of h. So correct that in the notes. Make sure you make that correction. This form was not right. So this should be the y partial of h. This should be the x partial of h here. Okay, so now that's right. So make sure to correct that. Okay. Well, now you could see, well, if the y partial of h is 0, then this right-hand side is 0. If the x partial of h is 0, then this right-hand side is 0. So this is actually just dx dt 0, dy dt 0. Of course, that's exactly what we did to find the stationary solution. So this is not a very deep fact just from that. Okay, and fact 2. Okay, if x of t, y of t is a trajectory, that is a solution, then h of x of t, y of t is constant. Well, this is just me saying that, well, any solution satisfies h of xy is equal to constant, and therefore h of xy equals constant, right, is telling me that if I graph that, that's telling me the behavior of these trajectories, these orbits. Okay, they are being determined in this way. Okay. And so, what this thing says, right, that h of xy is equal to constant, explains basically everything I need to know about the solution to this thing. What is this saying? Let's use our Calc 3 for a little bit. So h of xy equals constant gives me these trajectories. This is a level set. This is a level set of the function h of xy. We know from Calc 3 that the graph of h of xy, if I were to plot that, is some graph. I need 3 dimensions, right? I need 3 spatial dimensions in order to plot this graph. If I'm lucky and h is nice, this h plots like some surface, right, in space. Level curves then to the graph of h would be planes cutting through at different levels. These are the cross sections of this surface made by cutting through with planes that are parallel to the xy plane. So think of cutting through at different z heights, z equals c, or z equals 1, 2, z equals -7, that kind of thing. These all would generate some curves formed by the intersection of those parallel planes with the graph of h. Okay. All right, so then let's see how to draw this picture. Okay, so we are going to only consider systems whose integrals only have non-degenerate critical points. What is a degenerate critical point? Well, if we go all the way back to Calc 1, right, we had 2 different tests for taking derivative and analyzing critical points of the function and figuring out what happened at those critical points, right? So this is like the main thing we wanted to do with derivatives in calculus, is we wanted to take derivatives, set them equal to 0 in some sense, and find all the critical points. And then the problem is that just because a function has a critical point somewhere doesn't mean anything happens there, right? So at a critical point, maybe that function has a relative max, maybe that function has a relative min, maybe it has a saddle point, right, which can happen for functions of more than one variable. Maybe it has a saddle point, or maybe nothing happens there. That can also happen. Sometimes you don't have anything going on. All right. So it can happen that nothing goes on at a critical point. So we want to know what happens, right? There's a lot of options. And so we had two methods of testing this, right? In Calc 1, we had the first derivative test, which always worked, but was a little bit more annoying to use because we had to test the sign of derivatives on either side of a critical point. And then we had the second derivative test, which is actually nicer, but the problem is that it didn't always work. It didn't work if the second derivative at that critical point was 0. So that's an example of what we call a degenerate critical point in the higher dimensional case here. So there's the Hessian matrix. Okay, so the Hessian matrix Hess, or the book writes it as, maybe I'll write it as the same as the book does. In a lot of places you'll see Hess written here. So the Hessian matrix of H of xy is the function, we'll say del squared H of xy is a matrix. It is a matrix consisting of the double x partial of H in the first slot, the xy partial in the second slot, the yx partial in the third slot, and the yy partial in this last slot. This is the Hessian matrix of H. This is our analog of the second derivative of a function of two variables. Okay, we'll say that a non-degenerate critical point, x naught, y naught, is one such that the determinant of the Hessian matrix of H at x naught, y naught is non-zero. So we want the Hessian matrix to be invertible at the point in question. That is our condition. Okay. Now, it turns out that if we impose this condition, so we're only considering situations when this is the case, all right, then this gives us isolated critical points. So basically, if they're isolated, it means I can box them off, or I can wall them off from other critical points. They're not so clustered together that I can't separate them in any way. Okay. There's only 3 possibilities when I restrict my attention to such critical points. Okay, so a critical point can be one of 3 things. So a non-degenerate critical point of an H can satisfy one of 3 possibilities. So the first possibility, it can be a saddle point. Okay. All right, it can be a saddle point. Okay. In this case, x naught, y naught is a saddle in the phase plane portrait. So now good terminology is key here. There's a reason why we have these good, nice names here. Okay, x naught, y naught is a saddle in the phase plane portrait. Okay. Second option It can be a local minimum. This is going to give rise to a clockwise center when rho is positive and a counterclockwise center when rho is negative. Okay. So this gives rise to a clockwise center so clockwise center when rho of x naught y naught is positive, counterclockwise center when it's negative. And lastly, it can be a local max. In this case, I just reverse these things. So it is clockwise when rho is negative and counterclockwise when it's positive. So clockwise, center, when rho of x naught y naught is negative, counterclockwise otherwise. And rho can't be 0, so you will get a determinative thing out of this. Now, you might say, well, how do I know which of these cases happens? Well, there's two things you can do. You can either remember how this worked in Calc 3. What's the determinant of the Hessian? Let's just write it, right? Determinant of the Hessian is the double x partial of h times the double y partial of h minus, for h that we're talking about, hxy and hyx are the same thing. They commute. Okay, so this is hxy squared. You had a name for this in Calc 3. What was it? This is the discriminant. You called this the discriminant d of xy. And it was d being positive or negative, and then some other things going on, that allowed you to apply what we call the second partials test in Calc 3 to figure out which case you were in. Non-degenerate just included, that gets rid of the case when the discriminant's 0, where you can't say what's going on. Okay, but there's an easy way to do this in terms of eigenvalues. Okay, so it turns out, here's how to know what happens at each critical point. Okay, so 1, x naught y naught is a saddle point if and only if, or exactly when, the Hessian matrix at x naught y naught has one eigenvalue of each sign. Okay. All right. All right. So you might say, wait a second. Eigenvalue of each sign. This is a generic 2 by 2 matrix. Well, seemingly. So this thing could have complex eigenvalues. So how do I even know that I'm in a situation where I don't have complex eigenvalues here? Well, this is a symmetric matrix. hxy and hyx are equal to each other. So this is a symmetric matrix, and it's a fact from linear algebra that symmetric matrices can only have real eigenvalues. So your eigenvalues are guaranteed to be real here, so this statement is not nonsensical. Okay. X naught y naught is a local minimizer when the Hessian has two positive eigenvalues. And 3, this is a local maximizer when it has two negative eigenvalues. Both eigenvalues are negative. So those are the cases, and that's how we figure out what's going on here. Okay. All right. So, you know, you can characterize this, of course, in terms of the determinant and trace of the Hessian matrix. So this puts it as the discriminant, okay, of the polynomial in question. This is really the discriminant, is what's going on here. And so there are quicker ways of testing this, of course. So it's a saddle point when the determinant is, so saddle point is when the determinant of Hessian is negative. It is a local minimizer when the determinant's positive and the trace is positive. And it's a local maximizer when the determinant is positive and trace is negative. And those are my only three options. So let's see how this works for our key example. So sketch a phase portrait sketch a phase portrait for the system dx dt equals y, and dy dt is equal to 4x minus x cubed. Okay. So we already saw that this is a Hamiltonian system. This is a Hamiltonian system with integral or Hamiltonian h. I have a cat I have to remove. Hold on. Okay, hold on. There we go. All right. Sorry about that. Okay. So we have Hamiltonian. This is a Hamiltonian system with Hamiltonian h, which is 1/2 y squared minus 2 x squared plus 1/4 x to the 4th. Okay, we've actually already found the critical points for this thing by setting these things equal to 0. We already found stationary solutions and thus critical points of h. So this is the first thing we did. The stationary solutions for this we found are 0, 0, minus 2, 0, and 2, 0. Okay. All right. The Hessian matrix in general Remember, this is the h, the double x partial of h, the xy partial of h, the yx partial of h, and the yy partial of h in this 2 by 2 matrix. So the xx partial of h, what is this? So here I'm going to get minus 4 plus 3x squared. Right? So this is minus 4 plus 3x squared. If I take the x partial of h, I get something, so this y term goes to 0, and I get some things in x. Then I take the y partial, I get 0. Okay, similarly, if I take the y partial, these two terms go to 0, and I have only something that depends on y. Then when I take the x partial, that becomes 0, so this is 0. Of course, I know that these should be symmetric. I'm just checking. Okay, so once I find that that's 0, I automatically have to know that that's 0. And then lastly, my double y partial is these two. The y partial of these two things is 0. This would be 2y, and then, sorry, 1 times y, and then it'd just be 1. So there's my Hessian matrix. Okay, well, let's plug in our critical points into this Hessian matrix. So there's the Hessian matrix at 0, 0. What does that become? That becomes minus 4, 0, 0, 1. And plugging in at either plus 2, 0, minus 2, 0 doesn't matter, because the only thing that gets plugged in there gets squared, so these are actually the same. So the Hessian at either plus or minus 2, 0 is the same thing. I get 3 times 4 plus minus 4, so that's 8. So this is 8, 0, 0, 1. Okay. Well, this means that 0, 0 is a saddle point. Why? Because I have a positive eigenvalue and a negative eigenvalue. Remember, I have a diagonal matrix here, so the eigenvalues of this matrix are just minus 4 and 1. So it has a negative eigenvalue and a positive eigenvalue, so saddle point. What about this one? Well, this thing has 2 positive eigenvalues. Okay, so what do I get there? I get local minimizer. Okay, so I get local minimizer, so plus, minus 2, 0 are local minimizers. Okay. And here, remember, rho, since this is a Hamiltonian system, rho of xy is just equal to 1, so that's always positive. So I have a saddle point, which leads to a saddle in the faceplane portrait. I have a local minimizer with rho always positive, which leads to clockwise centers. So I have saddle point and 2 clockwise centers. So what does my phase plane portrait look like? So here is my point 0, 0. Here's my origin. I'm going to very lightly draw in the axes. Very lightly, because I don't want these to get confused for trajectories. All right, so I'm going to very lightly draw in axes. But these are not any piece of trajectory curves. So there's my axes. So here's the point 0, 0. Here's the point 2, 0. And here's the point minus 2, 0. Okay. Should have probably given myself more room here. Maybe I'll do that here. Let me do it on the back. Okay, so let's do it on the back here. So here's my very light axes. Okay. So here's my 0, 0. Here's minus 2, 0. And here's 2, 0. Okay. So 0, 0 is a saddle point, which means in the phase plane portrait, near that it should look like a saddle. What did a saddle look like? Well, I had these eigen solutions, right, coming in like a crisscross here, with some moving away from origin and some moving towards, right? These should be clockwise centers because both of them are local minimizers. Rho is 1, which is always positive, and local minimizer is clockwise center when rho is positive. So these are centers that are clockwise. Of course, I'm drawing them counterclockwise. That's pretty funny. But these are clockwise centers. Same thing over here. Now, how can I finish this picture? Well, the way that this actually looks is something like this. So that trajectories on the outside look something like this. They need to respect the direction here indicated by these things. So this trajectory is going around here, around here. Notice the directions match up. Okay. There's another trajectory, right? And here's another trajectory around that critical point. So it looks something like this. Okay. Now, what is this thing actually saying? All right, what is this? Well, I mean, other than giving me just an explicit picture of the trajectories in question, what is a way of seeing what these trajectories are? So I recommend looking at, this is page 17, and this is chapter 3, section 8. Okay, and so what is this picture? So this picture in chapter 17 is real, or sorry, in page 17 of 3.8 is really, really nice. But basically what it is it's taking h of xy. So recall, h of xy was found to be, well, here, I'll do it on the other page. So h of xy is 1/2 y squared minus 2x squared plus 1/4 x to the 4th. What does this look like if I plot it, right, in space? Well, in space, if I try to plot this thing, what it actually looks like is something like this. It is this kind of double dipped surface, right, that looks like kind of two of these sorts of paraboloids with a shape, if I cut through it up here, that looks kind of like this. Okay. So that now it's actually symmetric. I drew it here looking like it doesn't come nearly as far down here. The idea is that if I have a cross section, so if I have a cross section of a plane, formed by plane cutting through here, I'm only going to get these disconnected curves here, right, above minus 2, 0, and 0. 2, 0, and minus 2, 0. Okay. At like this point, so this would be the level curves that I get h of xy equals like c1, right? H of xy equals c2 maybe cuts through exactly here at this level that gives me this pinched thing. Oh, I didn't go all the way. Right. Gives me this pinched thing. And then, of course, that would be a height h of xy is equal to like c2, some other height. And then, of course, if I go all the way up here at the top, some level h of xy is equal to c3, I get this curve. And then if I think of taking all possible level curves formed by these intersections and projecting them down onto the plane, what do I get here? So the curves like this look like this. Forget about the direction. This curve looks like this thing. And this top curve looks like... So past a certain level, all the trajectories start looking like that. But that's exactly this picture. Now, if this image confused you, look at the one that's a lot more nicely drawn in this section. But now we see, drawing a phase plane portrait, basically I pieced together phase plane portraits from my linear cases here just at these pieces. Now, this is for a really, really nice type of system where we have a Hamiltonian or we have an integral for the thing. And so these things can only look a certain way, all right? So you don't get a whole lot of variety in how this looks. We are going to finish this discussion tomorrow with moving to non-integral methods that do not rely on having an integral. So in the last lecture, in the final lecture tomorrow, we will cover how to mimic this analysis for a system with no integral. Okay, or at least one that I don't know how to find. Okay. And that will be it. That will be the final topic in the course. All right. So anyway, that is the plan. Okay. So I will see you all for the final lecture tomorrow. I'll be posting some announcements, reminding you about this final assignment schedule and how this goes. And I'm also going to hold office hours tomorrow, so I'll send a link for those a little bit later. So anyway, that is the deal. If there's time in the last class, show my face. Okay, all right, I will show, and I'll show the cats too. So yeah, in the last class, I typically do that in these online classes for the last class, but I'll do that for the last lecture, maybe at the end of class. So anyway, I will see you all then.